Everything seems to be in order here. All right, hello everybody. Welcome back. All right. Just got some more people coming into the waiting room. So once everybody's here, we'll get going with chapter 1 from Dusek's textbook. All right. Everybody's slowly making their way here. Let's see, we're at 49. It's probably time to start, but maybe we'll wait just another minute or two because more people are slowly making their way into the waiting room. Okay. All right, 50 people. That's enough people. All right, well, so I hope everybody's doing well today. Can everybody hear me? Awesome. All right, great. So we're ready to get started, and today we're going to be covering hopefully the first half of the first chapter. The first half, the material that we'll be covering today is dealing a lot with just what exactly science is. I imagine if you're in this class, you've probably thought about this to yourself in connection with the question of what technology is at some point or another, maybe in the run up to this class, or maybe in the distant past or something. But just what is science? I think a lot of us have, if we're non-scientists, have an idea of what science is that is maybe not the best representation of how science is actually done nowadays, or has been done. So the idea today is to look at how science has changed from the early modern period up until the present time. How have we understood what scientists are doing? How have scientists understood what they are doing themselves? And so on and so forth. And of course, science can be traced much farther back than Dusek does in this first chapter. Right, the actual roots of science can be argued to go all the way back to the ancient world. What Dusek is talking about is modern science, but there are some really interesting really interesting moments in the history of science that you can learn about in ancient Greece and ancient India, in the ancient Middle East, and those are all really cool to learn about. But we're not going to have time to talk about that. So how does Dusek start? Well, he mentions in the opening of chapter 1 that a lot of philosophy of technology that we did or started doing in the 19th and 20th centuries actually paid very little attention to the philosophy of science. And he discusses the reasons why in this paragraph, which I will read to you. So why haven't philosophers working in the area of philosophy of technology paid much attention to philosophy of science? Well, because if science, I'm quoting directly here, is simply a direct, uninterpreted description of things as they are, untainted by cultural and social biases and constraints, then science is simply a mirror of reality. Furthermore, if technology is simply applied science, and technology is fundamentally a good thing, then there are no special philosophical problems concerning technology itself. That is, the frameworks for the development of technology and its reception are not of interest. There are only after-the-fact ethical problems about technology's misapplication. However, recent approaches to the philosophy of science have shown that science is laden with philosophical presuppositions, and many feminists, ecologists, and other social critics of science have claimed that science is also laden with social presuppositions. Many recent approaches to philosophy of technology claim that technology is not primarily, or even is not at all, applied science. So we want to look at this sort of latter bit today. How did the understanding of science start to change in the 20th century such that we became aware of, say, the influence of, philosophical presuppositions, cultural influences, so on and so forth? How did we start to become aware of that? That's what we'll look at today. Before we do that, I kind of want to kick a question over to some of you, and I would like to ask you all, we've still got people pouring in. Here we go. So you can answer in the chat or in video or audio form. But I'm curious what you guys think of this. Some of you may have this picture of science, and I know that in the past, I've actually been guilty of this too, in my undergrad years, of thinking of science as this sort of, paragon of rationality, this completely unbiased, objective picture of the world. Science is the best picture of reality we have in many ways, whether you believe that science is a perfect mirror of reality or not. But I think it's also pretty easy to come up with examples of sort of what Dusek is talking about in the latter part of this sentence. So I'd like to kick this question over to some of you. What do we think of science? What is science? What are we doing with it? Is science the best mirror of reality? Or is it just something humans do? Experimenting. Oh, lots of stuff coming into the chat here. Okay. So experimenting, yeah, so that would be like scientific experimentation. Science is evidence of things, a tool to discover truth, a tool for understanding the natural world, something humans create to make sense of the world around us, like math. Yeah, okay. Lots of good stuff here. Yeah. A way to study material reality, anything measurable. Science is a way of proving things wrong. Yes, actually, we're going to get to that. I'm glad somebody mentioned that. A higher framework for comprehension. Way humans evolved to the scientific process. And the scientific process has itself evolved, as we'll see today. An extension of the mere exposure effect / hypothesis. So a lot of different answers here, but I do see some common themes. Oh, this is really good. Amia says here, there's a flaw in assuming that science is objective when the measures we use are by nature constructed. Yes, exactly. Stuff like this is what we started to sort of think about in the 20th century. we started kind of realizing that, wait a minute, science is just a human activity, right? It's a bit of both. Seems like we try to make sense of the world by both familiar and ever-changing framework. Yeah, that's a good way to put it, I think. Science is always sort of changing because it's something humans do, right? You know, oftentimes, method versus an institution. That's a good point as well. And we'll talk a little bit about some of these institutions versus methodologies as we make our way through the material. I'll give you my little undergrad Josh spiel here. And that was when I was doing my undergrad, it was the height, or not the height, but rather the very beginning of the new atheism in the popular discourse, right? So you had figures like Richard Dawkins and Sam Harris and those guys, right? Which are not philosophically rigorous people by any stretch of the imagination. You know, going on and sort of criticizing religion as, you know, as some flawed human practice, a way that's not good at getting at the truth, and then casting science as something that's perfectly rational and objective and always gets you to the truth. And over the years, I've kind of increasingly gained an appreciation of just how simplistic an outlook that is, right? Yes, I do still think that science is the best picture of reality that we have. But I kind of think of science in the way that Winston Churchill thought of democracy, right? There's a famous quote from Churchill, right? Democracy is the worst form of government, except for all of the other ones. Maybe science is a little bit like that. Science is not perfect, but it is maybe one of the best tools we have. But we need to be aware of when it's not working right, or when we're not thinking of it properly. Let's get these people into the waiting room. Hello. So let's move on to the next slide and see what Dusek has to say. Yes, inductivism. This is fun. Just try to move my thing out of the way there. Now, inductivism is where Dusek starts off next. And inductivism is probably one of the most influential and widely understood ways of thinking of science. And this view is due to a fellow named Francis Bacon, who is pictured here. He lived from 1561 to 1626. He was an English scholar and politician. He was even a nobleman, I believe. He was the Viscount of something or other, quite a fancy title. And he's generally considered the father of empiricism and of the scientific method. The scientific method, by the way, that Bacon is known for is not the scientific method that you would have learned in high school, right? What's the scientific method that you learned in high school? Anybody remember? We'll see if anyone offers an answer in the chat.
Would it be to pose a question, a claim, have an hypothesis, then have some type of protocol to verify that hypothesis, then analyze the results and have a conclusion?
Basically, yes. Like as you said, you're Julien, that's who was talking? Yep. Okay, yeah, as you said, that's basically how we think of the scientific method now. And a lot of people in the chat said pretty much the same thing. Zach said hypothesis, experiment, evaluate, hypothesis, observe, conclude. Really what we do is we start with observation. Then we form a hypothesis, and then we test that hypothesis. Jonah says Aristotle, question mark. I like that, because actually Aristotle represents a completely different scientific paradigm, and we're going to hopefully talk about paradigms in a sec. Yeah, I mean, Aristotle is not a scientist by today's standards. He's straight up a philosopher. But back in the day, Aristotle was what the ancient Greeks would have called a physikos, someone who studies nature, a natural philosopher. And natural philosophy is what turned into science. Aristotle has way different ways of understanding causality and how the world is put together than we do. But when we move on to talk about the work of Thomas Kuhn, we'll see why this isn't as wacky as it might seem to a modern scientist. Now, so that's the modern scientific method. The method that Bacon is famous for is promoting this inductivism stuff, right? Inductivism, using induction to learn more about nature. And this is why he's the father of empiricism too, because to use induction, you actually have to go out and look. You have to observe the world. And empiricism, in case anybody's not familiar or needs a reminder, empiricism is the philosophical school that says that the primary source of knowledge is the senses, right? And it's usually contrasted with rationalism that says the primary source of knowledge is reason. So what does Dusek say? He says on page 6, according to inductivism, one starts with observations of individual cases and uses these to predict future cases. So the scientific method that Bacon is known for is all about using the induction. We call it the inductive method. We use inductive reasoning to thinking about the natural world. Now, just in case, let's talk about induction. Philosophers talk about many different kinds of reasoning, and induction is just one kind of reasoning. We've got induction, we've got deduction, we've got abduction, right? All these different kinds of reasoning. But what is induction? Does anyone want to try to, say, offer a description or perhaps an illustrative example that can explain what induction is all about as a sort of reasoning? Here we go in the chat. Well, kind of. Let's see if we can make it more concrete. Yeah, okay, so, oh, there's a lot of answers coming here. Okay. So if you prove one case is true, then you can assume the other must be true based on that. That's related to what Tess says below, I think, what Umay says here and what Tess says, reasoning from the specific to the general. Yeah, proving, well, proving is problematic, as we'll see in a moment. Yeah, like so we're getting all of these answers kind of capture a bit of what induction is about. Induction is what's not emphasized in those answers is that I think induction is very empirical. And it's the form of reasoning that a lot of empiricist thinkers tended to use, right? Looking at the world, reasoning about individual cases and trying to generalize, right? That's what the empiricists were all about. Rationalists were, of course, all about induction or deduction. So rationalists are doing like deductive reasoning, like you know, like the deductive syllogism kind of stuff, right? Socrates is a man, all men are mortal. Or I guess I flip those around. All men are mortal. Socrates is a man. Therefore, Socrates is mortal, right? That's a deductive argument. But inductivism, you look at the world and you try to generalize laws from individual cases, right? So I'll describe here this bottom bit first. Or no, let's do the top. The interesting thing about Bacon is he discusses these idols, you know, that actually are sources of pervasive bias in our reasoning, and they prevent us from theorizing properly. They prevent us from observing without bias. So these idols are things like religion, perhaps, or even philosophy. Bacon counted philosophy among these idols, and I think that's probably because the philosophy up until then in Europe had been primarily like scholastic philosophy, so like Thomas Aquinas, stuff like that, and it was all just metaphysics, right? Metaphysics. How many angels can fit on the head of a pin, and all of that kind of thing. And I think Bacon saw that as antithetical to understanding how the world actually works. So he kind of wants to get rid of metaphysics and just use induction, right? So that's the inductive method, or inductivism. And as I said, and as many of you were saying, it involves looking at the world and generalizing individual cases to laws of nature. And the more individual cases there are that fit the generalization, that is your law, the more probable it is that the generalization is true. So for example, maybe I'm a natural philosopher and I'm studying swans, right? And I look and I see a white swan. Okay, here's a swan over here. It's white. Okay, cool. I observe another swan the next day. It's a white swan. Okay, cool. I'm out there with my little bird book, finding swans left, right, and center. They're all white swans, all with white plumage. So I generalize to not quite a law of nature, but a regularity that I'm observing. All swans are white. But this is because every swan I have encountered has been white. We could prove my generalization wrong or refute it by finding a swan of a different color. Perhaps I encounter a black swan, and all I need is to find one. And then I know that my generalization, all swans are white, is false, right? So that's induction. So that's what science was about for a long time, probably up until the early 20th century. Science was very much about inductionism or inductivism, especially British philosophy, right? Even scientists, famous 19th century scientists, right up before we get to the 20th century, we've got thinkers like Michael Faraday, the Cinderella of science, right? Michael Faraday was not educated in mathematics. He came from, an underprivileged sort of working class background, and he went on to become a very, very good scientist. He did a lot of work with electricity. Faraday is known for answering Queen Victoria when she asked, "What use is electricity?" Faraday replied, "What use is a newborn baby?" Right? We've got this new thing we know about, electricity. And he did so many experiments, helped people understand what electricity is, did a lot of public demonstrations, science demonstrations. He was a prolific sort of popularizer of science. And he often claimed to be completely unbiased, to just use inductive reasoning, logic, when in fact, if you read his work, there are actually quite a lot of interesting metaphysical speculations there. So even though not all scientists were strictly inductivist, they pretended to be, right? Similarly with Charles Darwin, who's known for describing the theory of evolution by natural selection, right? Charles Darwin similarly claimed to be free of bias, just rational observer, inductive reasoning, but actually a lot of what Darwin did depended on a type of reasoning called abduction. Abduction is when you come up with a hypothesis that best fits the facts, or not necessarily a hypothesis because you're not testing it. Rather, abduction is more like the argument to the best explanation. How do I best explain all of the things that I'm observing? That's abduction. So these are the idols of Faraday and Darwin, right? Or what Bacon would have called idols, I suppose. So what's the problem here, right? Are there problems with inductivism? Yes, in fact, there are. Inductivism is still probably the most widely believed way of understanding science, at least amongst the public. Right? What do scientists do? Well, they go out, observe the world, and try to come up with laws of nature. Pretty inductivist. But inductivism actually suffers from pretty important problems. And the most well-known of these was identified by David Hume. It's called Hume's problem, or sometimes the problem of the justification of induction, right? What's the problem? Well, the problem is that, sure, induction works, but we tend to use it. We, scientists, tend to use it because induction is, we use it out of habit or custom, not because it is well justified in the epistemic sense, right? George Santayana, another philosopher, called this animal faith. We just kind of believe in induction because it's what we do, right? Now, why do we do this? Why do we have this scientific custom of using induction, right? How do we justify it? We justify our use of the inductive method by saying that it has worked in the past, right? Induction worked in the past, so it should work in the future, right? But this is itself inductive reasoning, right? So do you see the problem? The problem is that the way that induction is justified, or has been justified, Hume is arguing, is by appealing to induction, and that's circular. So we're trying to justify the use of the inductive principle right here by appealing to the inductive principle. And that is a problem because that's circular reasoning. And Hume pointed out a lot of problems like this in science, right? Later, other thinkers would kind of jump in and try and remedy the situation, if you like. Most famously, probably, is Immanuel Kant, right? Immanuel Kant, who was awakened from his dogmatic slumber, as he says, by reading Hume. Kant came along and argues that, well, maybe we should just give up the idea that the regularity that induction works on, you know, regularity in these individual cases in nature, allowing us to generalize into laws. Maybe that regularity is not in nature. It's not in nature. It's not in the things themselves or noumena. Rather, Kant says, they are imposed by the mind. And if you're not familiar with Kant, this is going to sound really, really weird. But things like space, time, causality, length, width, solidity, duration, these are all kind of structures the mind imposes on reality rather than structures that are there in reality. According to Kant, we can't really know about the things in themselves anyway, the things in themselves, the noumena. We can only know about the phenomena or things as they appear. That is how they appear in the mind. And it's the mind that imposes this regularity on the phenomena, the appearances, right? Our perceptions, basically. So I know that probably sounds kind of weird, and it is, but that's what Kant does. Later on, Karl Popper, 20th century philosopher of science, would just give up the claim that science involves induction at all. He would say, we're not doing inductive reasoning when we do science. We're not trying to verify things when we do science. What we're doing is actually we're trying to disprove our laws and our theories when we do science. That's actually what we're trying to do. So those are some problems with inductivism. And a few tentative answers, although, whoops, we'll keep exploring. Whoops, oh God, my slides are going all over the place here. Okay, but we'll keep exploring. We get into the 20th century now. Now, in the 20th century, we have logical positivism. This came out of Europe in the 1930s, and it's primarily associated with the Vienna Circle. Today, a group of philosophers that were working in Vienna, Austria at the time. And these were, you know, not strictly philosophers, but they also did physics, mathematics. They were very much scientists as well as they were philosophers. Here's a picture of the mathematics seminar room at the University of Vienna, where the circle would begin meeting all the way back in the early 20th century. This is prior to the 1930s. This is in I think all prior to the 20s even. So anyway, the Vienna Circle develops this school of thought called logical positivism. And eventually, with the rise of Nazism in Germany, a lot of these thinkers fled Austria because Austria was annexed early in the days of the Second World War by Germany. A lot of these thinkers fled to Europe, or not Europe, the United Kingdom and to the United States. And that's why, that's kind of why we have this divide today. We have Anglo-American philosophy or analytic philosophy, which kind of grew out of this. And then we have the continental stuff, right? The critical school, postmodernism, phenomenology, stuff like that. So that's part of why this divide exists. So the thinkers of the Vienna Circle left Vienna with the rise of Nazism, and their thoughts began to spread into the English-speaking world, into the United Kingdom and the United States. Let's see. My computer is slow, so I apologize if my screen is getting choppy here. So what is logical positivism all about? Let's make sure I'm on the right slide. Yeah. Well, according to Dusek, logical positivists thought of what they were doing as the highest form of knowledge. He writes, and I quote, "They saw statements other than empirically supportable ones as meaningless. This was the verification theory of meaning. For a statement to be meaningful, it had to be possible to verify it, to show it true by empirical evidence. And of course, this excludes fields like theology and metaphysics. Theology is, of course, a little bit about outside of the scope of this class, but theology we could think of as the study of God or the study of the divine. And of course, metaphysics is the study of reality. That's how I like to describe it. Metaphysics, to give you the Wikipedia definition, is the branch of philosophy that asks questions like what kinds of things exist and what are they like, right? What exists and what is it like, right? These two fields are kind of tossed out by the logical positivists. It's like, well, we can formulate statements in theology or metaphysics, but we can't verify them, right? And for logical positivists, language, this is just a little digression on language, but language is so important for the analytic tradition. Does anybody know why? I'll just hang on a second in the chat. Maybe somebody knows. We'll see. If not, I got you. I can explain it. But well, I'll give it a crack. I'll take a crack at it. Okay, so language. Why is language so important? Language is kind of what connects the mind to the world, right? Language is what connects the mind, the mental, to the world. And we can say things about the world with language to express, our thoughts, to express our thoughts to others, as Descartes famously said. So language is important because of that. And language is important because I can formulate statements about the world with language. And these statements are called propositions, right? You've probably heard terms like propositional logic. Propositions, statements. Yeah, exactly. Dula says here in the chat, language can help us understand how we see the world. Well, language is perhaps, maybe it's a tool, maybe it's a natural phenomenon, but language is how we understand the world amongst ourselves, right? So I can come up with statements about the world, and these statements can have a truth value, right? Let's say I utter the following proposition. I utter, "It is snowing in Ottawa." That's a statement about the world, and it could be true or false, right? In fact, if I look out my window right now, I see that it is not snowing. So the statement, "It is snowing in Ottawa," has a truth value of false. It is false, right? And I can show that by empirical evidence. I can go, just look out my window here. It's not snowing. So there you go. True statement. We can't do that with statements like, what's a theological statement? A theological statement is, God loves you. Okay, but the logical positivists would say, well, we can't show that that's true with any empirical evidence. We can't show that that's true. So we're not gonna worry about any of that. We're only going to look at stuff that we can show that we can demonstrate is true with empirical evidence. Same with metaphysics. Metaphysics. Maybe in metaphysics you're going to talk about something like free will. Free will is a very metaphysical idea. Human beings have free will. Is a statement that perhaps the logical positivists would have seen as meaningless, because it's like, how do you empirically demonstrate that people have free will? I mean, you can kind of weigh in on this empirically once you get a little bit later into the 20th century, once you find once you start looking at neuroscience and stuff like this. But anyway, at the time, maybe this would have been a metaphysical question that would have given them pause. There, of course, they're probably talking primarily about the metaphysics of the pre-modern period metaphysics, how many angels can fit on the head of a pin and that kind of thing. Here's a question. Wouldn't the senses be the ones to understand world? Language is used to describe observations to others. Yes, but with language, we can actually communicate our thoughts, our concepts, everything that's important to one another, right? There's a limit to what you can do without language. Without language, you can point to things and, do stuff like that, but you can't really reason. You can't really reason the way that we reason with language if you don't have language, right? Oh, that's a good question from Dula. Would a common example of metaphysics be the Big Bang Theory, or is that more theology? Technically, the Big Bang Theory is what is called cosmogony, which is the study of the origins of the cosmos, right? Some people might say it's theology. I mean, Fred Hoyle, the famous astronomer, he actually came up with the name Big Bang because he thought it sounded silly. Fred Hoyle thought that the Big Bang Theory was just a religious explanation. Poof, God creates the universe. It's silly. It's the Big Bang. It doesn't make sense. He actually thought it was silly. But now we know, as Zach says, we do have some very good empirical evidence that supports the Big Bang Theory, right? But at the time, this probably would have been a metaphysical question, where the positivists would have said that, well, we don't have any evidence, so we can't. Let's not worry about it, right? So that's what I would say about that. Now, the funny thing is about the Vienna Circle is that a lot of them held reformist political views, even social democratic political views, but they didn't think of political philosophy as, scientific philosophy, in the sense that we can't verify statements in political philosophy the way we can verify scientific statements, but they might have gone too far. But so here's an example. Yes, it may or may not be, right? We don't know what happened. We don't know what led up to the Big Bang, right? We don't know. As we get closer to T0, as we go back in time, the laws of physics kind of start doing funny things, and we don't actually understand how things work as we get closer to T0. What happened before the Big Bang it depends who you ask, right? Some people will just say nothing. Some people would say that since the Big Bang at T0 is the beginning of time, that it doesn't make sense to ask what happened before the beginning of the universe. That would be like asking what's north of the North Pole. Well, nothing. It's just, you just start going south again, right? So it's a mystery. It's presently a mystery. Yeah, but what is nothing? What is nothingness? Is nothingness a thing that can even exist? Does that make sense? Physicists will say like, oh, well, the universe came from nothing, but the nothing they're talking about is a quantum vacuum. And a quantum vacuum is not nothing. It's a quantum vacuum, right? So maybe they should read more philosophy of science, these guys. I don't know. Yeah, the absence of something, but a quantum vacuum isn't the absence of something. And yeah, Jared, you're right. There is a theory that the Big Bang might repeat itself, you know, expand, contract, Big Bang, big crunch, Big Bang, big crunch, right? So we don't know. There's also the theory of Lee Smolin, a physicist at the Perimeter Institute in Waterloo, actually, has a really interesting theory called fecund universes, where new universes are actually spawned within black holes. So our universe, our Big Bang, maybe we're inside of a black hole that came, that's in a different universe that was spawned by a different black hole or something. It's a very interesting theory. But notice, what would the positivists say about that? They would say, this is metaphysics, man. What are you doing? You can't verify any of these statements, Dr. Smolin. So they would say, but this is nonsense. Why are we talking about this? Right? Even though it is fun to think about. So Tess asked, would a positive be against making scientific claims about the past? Well, I think they might depend. It might depend on what kind of evidence that we have, right? If we have good evidence, like archaeological evidence or textual evidence, then I think that would count as some kind of verification for a statement about the past. But there's a lot of things, of course, we can say about the past that we can't know with certainty, right? So, yeah, they were really only interested in statements that could be verified. Anything else, they were like, bullshit, you know? But they may have gone too far with this, you know? Dusek says that the positivists are essentially committing the fallacy of persuasive definition. And you can, this is one of the reasons why, as an undergrad, I kind of didn't spend too much time reading the New Atheist books, because they kind of do the same thing, some of them. They define meaningless in a technical manner, right? Like a statement like, I don't know, Jesus Christ had brown hair is meaningless in a technical manner to a positivist, perhaps, because we can't go back and look, right? We can't get in our time machine and go see what color hair Jesus of Nazareth had, right? Sure, we can look at paintings and stuff, but those are by European artists who weren't there, right? So that's meaningless. But then to go ahead and turn meaninglessness from a technical definition into a pejorative, dismissive definition equivalent to worthless or garbage, right? The positivists were kind of guilty of that. And so were, I think, the New Atheists, a lot of them. Maybe not Dennett, but the other three for sure. So induction from that type of evidence is all good. Direct observation not required. Well, like, again, it depends. It depends. Like, I think direct observation is way too strict for a discipline like history, right? But for science, yes, direct observation, but not with the intent of generalizing to laws, with the intent of verifying those statements, right? So for the positivists, what we want to do is be able to verify to show that statements about the world have a positive truth value, right? How do we really do that, though? How do we put the logical in logical positivism, right? Well, we take inspiration from thinkers like Bertrand Russell, right? Bertrand Russell was a famous logician. A logician is like a mathematician philosopher, right? And he tried to reduce mathematics to logic. And logical positivism tried to do something similar with scientific theories. They tried to reconstruct scientific theories using formal logic. So the positivists really understood science. This is less about the methodology per se and more about science as a human practice. Science is really a collection of statements or propositions. And scientific theories are conceptual entities built up out of those statements or propositions, statements about the world, right? So scientific theory is very logical if you're a positivist. Maybe you have some axioms and then you have some statements and you can derive conclusions from those statements. And all of those statements are verifiable. So great, awesome, science, right? But things really didn't work out the way that the positivists wanted them to. Positivist philosophers were not able to work out a formal logic of induction. Why? Well, as Dusek points out, induction involves informal assumptions and judgment calls. And these are just not the kinds of things you could do in a formal system. A formal system, like logic, is a lot like math. There are rules you have to follow, rules of proper reasoning. And if you don't follow them, you're not doing it right. You're not going to come to the truth. But doing induction isn't like this, right? Doing induction isn't like doing like a logical calculus. It involves assumptions, it involves judgment calls. So, as Dusek puts it, the quest for precision and rigor led the positivists to self-criticism of their own empirical or observational criterion of meaningfulness. And this actually led to the rejection of verificationism. So, and I noticed this when I asked you all what science is all about. Some of you said, trying to prove things true, trying to verify things, which is a lot like induction, where induction is like, we try to look at the world and come up with general laws that describe how things behave. Yes, these are both aspects of science now, but they're not the core of what science is about. Scientists don't try to verify theories, for example. They verify individual observations, sure, but not theories. Theories, actually, we try and falsify. And that's what we're almost at falsification. We're almost there. That's what we're going to talk about in a moment. Anyway, the resulting position came to be called logical empiricism. So instead of verification, the positivists kind of loosened their criteria. They went from verification to mere confirmation and partial support for establishing truths about nature. Why? Well, as Dusek describes, empirical criteria of meaning tended to be either too narrow and exclude the more theoretical parts of science, or so broad as to succeed in allowing the more theoretical parts of science, but only to readmit metaphysics and theology to the realm of the meaningful. The original version of the verification principle excluded theoretical terms in physics, such as electron, as meaningless, while the principle would allow either this object is red or God is lazy to be verified by a red object, and hence allow God is lazy to be meaningful. I really like that one. So what are they saying here? Well, if we have to verify every single statement, well, then theoretical terms that we need to do science, like electron, that term is meaningless because we can't observe electrons. At least we couldn't at the time. We can kind of observe electrons now, I suppose, but observe is a strong word. Plus, quantum physics, weird stuff happens when you observe things for some reason. We don't really know why, but electrons at the time when people were doing physics were theoretical entities. They don't look like anything. Like we'll draw models of atoms. We'll have a nucleus with some protons and neutrons, and then some electrons going around. It's not what things really are like. These are just representations, you know, because electrons are really theoretical entities. And we need them, but the verification principle would make us exclude them. But it would allow us to include really weird statements like either this object is red or God is lazy. That allows the clause God is lazy to be meaningful if I can verify that there's a red object. Because God is lazy appears in the same sentence as red object, then if I go either this object is red, this is my thesis, it's red, okay, so either it's red or God is lazy. It's red, so God is not lazy. But that still means something, even when there's no empirical way of verifying the statement God is lazy or God is not lazy directly. Does everybody follow me there? I know this is kind of a weird example, but just make sure everybody understands. My red object back. Yeah. Yeah, I mean, well, what it means is like the statement either this object is red or God is lazy means something because I can verify whether the object is red or not. But because God is lazy is also in that same sentence, it becomes meaningful, even though I can't verify anything about God the way I can the red object. And that's why the positivists had to loosen their criteria from strict verification to just confirmation or partial support. So that's why they do that. Where are we next? Let's see, how much time do we have? Okay, we're actually doing pretty good for time. Come on, computer. Computer is slow. Ah, here we are. Karl Popper, the fun stuff. Well, I mean, in that statement, everything is meaningful, right? All humans are mortal. I'm a human. I'm immortal. Those are all verifiable, I would say, right? But the problem with the previous statement is that you've got something that's not verifiable that becomes meaningful by virtue of its association with a statement that is verifiable, and that's a problem. I could say something like, if I'm teaching philosophy of technology, then I'm a cheese sandwich, right? I mean, this is different because it is observational, but obviously I'm not a cheese sandwich just because I'm teaching philosophy of technology, right? Like an exclusive OR gate. Well, I mean, see, bananas are yellow and but these like, that's funny. So my walls are bananas. Yeah, I mean, but you can observe and verify or disprove, right, that your walls are in fact not bananas, right? But you can't do that with God, right? God may, like, let's bracket the question of God's existence. God may or may not exist. How could you verify something about God? You can't, because you need direct observation, right? So it's a problem if statements about God take on meaning or truth value by associating them or placing them in sentences with things that are verifiable, right? Because statements about God are not verifiable, right? Yeah, okay. So it's not quite, yes, exactly. And the part that's not verifiable is still meaningful because it's in that same sentence. And that's a problem for the positivists. It's too strict. It allows wacky stuff like that, like God is lazy, and it disallows important theoretical items like electrons, right? So that's why they had to change that. It's not quite, just to answer your question, it's not quite like an exclusive OR gate. It would be like, it's actually more like an AND gate, but if, no. See, I don't know. I don't know if logic gates really work as examples here, but I suppose if it were an XOR gate, it would. Okay. What we want in a sentence like that, like either, yes, it would be like, yeah. So just to bring it back to the exclusive OR gate, if I have an exclusive OR gate, I want A or B. I want A to be what's verifiable and B is what's not verifiable. And I want the exclusive OR gate to always pick A, but say it doesn't. Right? That's the problem. Right? But then again, I don't think that, I'm not sure if logic gates are, they might not be that illustrative here. So we'll come back to this later if we have time at the end of the class. So the positivists are kind of realizing the limits of their own project. And along comes Karl Popper, who was another Viennese philosopher of science. And he spoke with the members of the Vienna Circle. He knew many of them, debated with them, but he disagreed with them about some important things, right? He didn't agree with everything that the Vienna Circle members had to say about how science worked. Science is, in fact, not about verification at all, according to Popper. It's about falsification. And this is called the falsification criterion, right? On page 10, Dusek writes, Popper claimed that falsifiability, the possibility of being falsified or refuted, not verifiability, is the criterion that separates science from non-science. And the more falsifiable a theory is, the more scientific it is, in fact. And this is what science is really all about nowadays, is failing to disprove theories. If we repeatedly fail to disprove a theory, well, that theory probably does a pretty good job of describing the way the world is, right? So on this whole falsifiability project, scientific laws and not statements of fact are the most scientific statements, right? And this is how most contemporary scientists think of what they do. They think of it in terms of how Popper thought about science. Yes, there's still some verification happening. We have to verify particular facts. And some statements of facts will achieve varying degrees of probability being true. Think about my earlier inductive example, right? All swans are white. Well, that's induction, generalizing from individual cases to a switch to verification. That's a white swan. Yep, check it, look at it. Yep, it's a white swan, all right. And I do this, but then I encounter one black swan. And I check it. Oh, look at this plumage. It's very dark. It's definitely a black swan and not a white swan. So my probability of the statement all swans are white being true goes down a little bit when I verify this particular fact, that there exists at least one black swan, right? What's really, really big and important, again, are laws and theories. Has anybody ever heard this, right? Maybe you're on social media, or you're hanging out with some folks after a philosophy class or a science class, and maybe you're talking about something scientific. Maybe you're talking about, I don't know, the COVID-19 vaccines. Maybe you're talking about the theory of evolution was a big one when I was an undergrad. And somebody says, hey, that's just a theory, not a fact, right? Has anyone ever heard somebody use that rhetorically? Well, you can tell them next time, if they think that a fact is superior to, yes, exactly, Zach's got it, you need to stop them and tell them that they've got it backwards. Facts, who cares? I can come up with a fact about anything, right? It's a fact that my coffee cup is slightly broken. Ooh, so look at that fact. It's so important that facts, man. Facts are whatever, who cares? Could you call religion a theory? I'll come back to that. Let me come back to that one. But yeah, facts and theories. Facts are a dime a dozen, right? You can come up with a fact. Here's a fact, there's a fact. There's facts all over the place. Who cares? What's important, protected opinions? I'm not I mean, well, opinions are different than facts. So let me finish my theory fact spiel first. Facts are a dime a dozen, but we can use true facts to build laws and theories. Theories are like big frameworks of scientific laws that explain why the facts are facts. And that's why facts are important, but not as important as theories. So if someone comes along, if you're talking about like the theory of evolution, for example, and someone says, whoa, 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 it's the theory of evolution and not the fact of evolution, you can tell them they've got it the wrong way around, right? What's important is a theory. The theory is important, right? Theory of gravity, germ theory of disease, theory of evolution. We've got theories of electricity, right? We've got all of this stuff, genetics, quantum mechanics. And this is how stuff like this works because of a theory, okay? Not because of facts. Yes, because of facts, but more importantly, because of a theory. That's why we have cell phones, computers, coffee in environments where coffee plants cannot grow. It's how we've scienced the crap out of the world that we live in. You know, so just real quick. Yeah, can you call religion a theory? Not in the scientific sense. Yeah, I agree. I think I agree with what Max says. Not in the scientific sense. Because I don't think religion really tries to explain facts. And protected opinions, are they facts? I don't know. I mean, opinions can be true or false, and opinions are always, even if they are true, mere opinion. They're not supported. They're not justified typically in the epistemic sense. Whereas something like a true belief is an attitude toward a true proposition or a fact for which you have some justification. That's what we call knowledge. So yeah, I don't think opinions are facts, but true beliefs are about facts, if that makes sense. A true opinion could be about a fact as well, but it might not be well justified. Protected opinion, like, can you give me an example? Jonah, yeah. Well, this is where we're going to get to next time, is that, even though we're all trying to be as rational as we can be, we're all humans with different worldviews, different politics, religion, social outlooks, doing science, and that matters too, right? So I'll just continue with this because I'm worried that I'm going to run out of time. We've only got 15 minutes left. So yeah, theory is more important than facts, but facts are still important. Laws generalize to multiple cases. We don't verify them, right? Popper even calls scientific laws infinitely improbable because they apply to an indefinite range of cases, right? It's the facts that we verify. It's the laws that we try and falsify. And as Dusek puts it here, the positivist's view of science fits with the view of science as primarily a collection of facts organized and helpfully summarized by laws, while Popper's view of science makes science primarily a collection of laws, right? So it's not, if you're a falsificationist, it's almost like science isn't a body of facts at all. It's It's a collection of laws that describes the world, right? And this is the falsificationist method. And this is why Popper rejects what he calls the myth that science is really about induction. It's not about induction at all, he says. It's about falsification. And as I've said, as I've already said, what counts here is that hypotheses or theories or claims, whatever, withstand testing. They withstand the testing that they're subjective to. They fail to be falsified. If we fail to disprove something, we retain it in our theory. So science isn't about proving things true. Oddly enough, it's not. At least nowadays, it's not. Science is actually about failing to disprove things. And that repeatedly, if you do that a lot, that supports your hypothesis or your theory. All right. So, my slides to change here. Okay. I really need to get a better computer. Well, there's really, Emily, that's a really good question. There's really no, there's no enough is enough, right? I'll give you an example, right? Albert Einstein, awesome dude, came up with the general theory of relativity and the special theory of relativity. And he also won the Nobel Prize for coming up with the law of the photoelectric effect. And in the work for that he did, he actually helped lay the groundwork for quantum mechanics. So this is why Einstein is so important and still talked about today. He was very, 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 very important in this way. Now, well, I mean, Abraham, yeah, the positivists failed, but they're trying to verify, not falsify, right? And I think Emily is talking about falsification. And that's why I think Zach is correct here. Technically never, but people accept it once the probability of being wrong is close to zero. And that's the point I was going to make about Einstein, is that after he published his theory of relativity, it was empirically tested, right? People went out, they actually used the transit of Venus. So the sun, is there in the sky, right? And Venus will transit. It'll pass in front of the sun, right? And if you do things right, you can measure the way the light bends at relativistic velocities and the effect of gravity and blah, 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 blah. And you can test Einstein's theories this way. And this was done within the first few years of Einstein's theory being published. And people were blown away. They were like, holy moly, this theory describes reality. It works. But here's the thing. Here we are over a century later, and we're still subjecting Einstein's theories to tests, and we are still failing to falsify it. Still, which is awesome. So that shows you how powerful falsification is. This does not mean that Einstein's theory gives us a complete picture of reality, though. Relativity doesn't work for things that are very small, like electrons. We need quantum physics for that. Quantum physics doesn't work for things that are very big, like black holes. We need relativity for that, right? So it's not complete, but it works, and it works really well. Yeah, exactly, Zach. Yeah. Yeah, oh yeah, the atomic clock, that's right. Yeah, I forgot about the atomic clock. We can have an atomic clock on Earth and an atomic clock at a high altitude, and we can measure the difference owing to time dilation because of their different positions in the gravity well. Yeah, and we need to, yeah, technology keeps evolving. That's right. Like Zach says here, we couldn't have done a test of Einstein's theory with an atomic clock back in the day when Einstein was alive. We couldn't have done it, but we can do it now. So when we come up with a new technology, we might be able to use it to test a particular theory. And that's really cool. you know? So yeah, that's kind of like an example. And again, as Zach said, to answer Emily's question, we can keep on going at this forever. We probably will. But no scientist seriously questions Einstein's theories, because the probability of it actually being falsified at this point is just so close to zero that it might as well never be falsified ever, right? Yeah, and that's another good point, Zach. Gravitational waves. Now we're getting to the point where we have technology that we can test predictions, that were made all the way back in the day. We can only test certain predictions now, thanks to new technology. So yeah, that's an excellent point. My phone. Call 47. Oh, we better talk about realism and anti-realism real quick. I don't know if we're going to get all the way through Thomas Kuhn, but just real quick, realism and anti-realism describes a couple of interesting differences with respect to what science is doing. Scientific realists, Dusek writes on page 12, claim that theoretical terms in science represent or refer to objectively real entities, even if we cannot observe them. Anti-realists claim that the theoretical items are not to be taken to literally refer to objects or entities. And these are both known respectively as essentialism and instrumentalism about science. So realism or essentialism says that theoretical terms in science refer to real entities. So think of something like electrons, right? If you're a realist or an essentialist, you believe that electrons are objectively real, even if we can't directly observe them. If you're an anti-realist or an instrumentalist, you'll think of an electron more like a theoretical term. It's not to be taken literally. Like, we have this tool for thinking called an electron. It has certain properties, and we can use it to make predictions that turn out to be true. But are there real electrons? Who cares? What do they look like? Who cares? Nobody cares. We're anti-realists, So that's how they'd understand. Each of those would understand theoretical terms, respectively. So a realist thinks of scientific theories as kind of like pictures of the natural world, literally a type of picture of the natural world. And instrumentalists think of theories as tools for making predictions about the world. And each of these ways of thinking came together during the Renaissance. The Renaissance was kind of like, where modern science, I suppose, sparked, got that spark of life from, right? A marriage of metaphysics and technology, as Agassi describes. Agassi, by the way, was a student of Karl Popper. So we got the Renaissance. We've got the breakdown of class barriers. This is known as the Zilzel thesis. The breakdown of class barriers. Economic uncertainty meant that there were scholars and craftsmen both looking for something to do. The scholars, metaphysics; the craftsmen, technology. These practices came together, and we kind of, this is where we get the idea of the Renaissance man from, right? Like, think of somebody like Leonardo da Vinci. He was an artist and an engineer, right? He could understand Aristotle as well as he could build a bicycle, right? The Renaissance man, the coming together of metaphysics and technology, thanks to the breakdown of class barriers. And this is, where these kind of two different ways of looking at the world meet and kind of blend together. The differences are still there nowadays in philosophy of science. But in the actual practice of science, I'd say in the Renaissance, there's a little bit of a blending there. Now, we've only got 5 minutes left. So I wonder if I can, we better save Thomas Kuhn for next time. So Thomas Kuhn, I'll just say, Thomas Kuhn is very famous for his book, The Structure of Scientific Revolutions. Popper's falsificationism was an alternative to the logical positivist approach of verificationism. But another alternative was Kuhn's approach, which was a sort of historical take on how science worked. The interesting thing about Thomas Kuhn is he was trained as a physicist. Really cool. He had a bachelor, master's of science, and a PhD in physics. And what did he do with that? He went and taught philosophy, which is really cool. And he talked a lot about the history and philosophy of science, and he introduced this really cool idea called a paradigm, a scientific paradigm, which is a really neat way that we can understand how science works, what it's doing, how it changes, and it kind of opens the way to appreciating that science is not perfectly objective because it's practiced by humans with particular outlooks on the world, with particular social, cultural, religious practices. Kuhn kind of opens the way to that realization, and I think that's really cool. So I think that since we're nearly finished, I have too many more slides to finish today, so we'll probably wrap it up here. And on Tuesday, we will attempt to finish chapter 1. Now, I know that on See You Learn, I know that on Brightspace, I've got everything kind of broken down one chapter per week. I don't think it's going to stay that way. I think we're just going to kind of get as far as we can every lecture. So next week, we will probably finish chapter 1 and then start chapter 2. The week after, finish chapter 2, start chapter 3. We'll probably have to keep going through the semester like that, but that means that things will be a lot less compressed. So we'll just go as far as we can every lecture and leave it there. So that's all for today. Before I wrap it up, does anybody have any last minute questions? Okay. All right, remember that if you think of something, yeah, like if you think of something, you can always shoot me a message on Discord after the class, right? So yeah, absolutely. And I'll leave it there for today. And I will see you all on Tuesday. Okay, thanks everybody.
Thank you, Professor.
Welcome. All right. End transmission.